Hey guys, welcome to lecture series on Z transform. We have already uploaded plenty of the videos on our channel based on the Fourier transform, Fourier sine transform, Fourier cosine and their inverses. So if you are interested to see this video, do check in my playlist. So in my today's video, I'm gonna explain to you all Z transform here. First of all, we go for some basic prerequisites that the formulas, this concept we needed, okay, like we needed here as a binomial theorem or expansion for geometric progression or a series or a sequence expansion. This condition we needed here. Now see that guys, we are applying Fourier transform, Z transform on a complex terms, okay. So that means you need to have an basic prerequisites from the complex numbers, okay. Yes, this definition you need to know before you are applying, okay. Yes, now see that you must need how to remember Z transform can be applicable, okay, or we can solve discrete valued function. We can solve discrete valued function using Z transform, okay. So here I have some of the basic definition that I'm not going to write here. You all just need to know, okay. This one is the expansion for sine x, okay. So if you all are confused, okay, how to remember the expansion, we can see that 1 3 5 7 odd number to the power x divided by their factorial and plus minus, okay. So you can make some trick to remember this expansion, okay. Yes, similarly sin x expansion, cos x expansion, okay. So this one is the cos x expansion, x raised to 0 by 0 factorial minus x square by 2 factorial plus x raised to 4 by 4 factorial minus x raised to 6 by 6 factorial plus so on, okay. So this one is the actually expansion for cos x, term of a cos x, okay. Yes, sin x, cos x, you need to remember this one. So after that binomial theorem, we already familiar with this x plus y raised to n, okay. So take n the power of a first term, n c naught, 0th power of a second term, then increase n c naught as up to the ncn, like nc1, nc2, nc3 up to ncn, x raised to n minus 1 up to the x to the power 0, okay. Then y to the power 0, y to the power 1, y to the power n, okay. So you have to write this way as a binomial theorem, okay. Yes, now see that this one is the expansion for x plus y raised to n. So you can write x minus y raised to n also, okay. So instead of y you have to take minus y, then everywhere you have to replace as a minus y, okay. These are the basic things you need to understand here. We need to know that binomial theorem, okay. Yes, these are the concept from 12th standard guys, okay, not and difficult. After that 1 plus x raised to minus 1, this one is also geometric expansion, okay. Geometric expansion for infinite term, okay. When we have sum of infinite term, we write first term upon 1 minus their common difference, okay. Yes, so this one is the expansion for geometric. So you can take that geometric expansion. Now see that 1 plus x raised to minus 1, that means we write 1 upon 1 plus x. 1 upon 1 plus x means first term upon 1 minus common difference, okay. Yes, so we write first term minus, then you have to take the expansion here, okay. Yes, so if you don't remember the formula geometric expansion, so what you can do, you can write the sequence 1x, x square, x cube, x raised to 4 and up to the so on, okay. That means it goes to the infinity. And about their signature, when we have plus and minus, plus in the middle, minus in the power, okay. So we take plus minus, okay. And when we have both sign negative over here, so take everywhere minus, it is a plus. So plus 1 plus x square plus x cube plus x raised to 4 and so on, okay. Yes, and we have condition that modulus of x need to be a smaller than 1, okay. Obviously as the part of denominator we want the positive sequence, so that's why we are taking it as the mod x smaller than 1, okay. This one is a e raised to x expansion, okay. This one is a series expansion. Now see that guys, we are going to apply Z transform on the sequence means an order real or complex number, okay. An order real or complex number. So this one we write under the summation, okay. So we can expand the summation also, but we are going to apply Z transform on the sequence, like a sequence f of k. So a sequence can be written as 1 3 5 7, like such a way, okay. For example I given, okay. So we are going to apply Z transform on a sequence, okay. Yes, now see that this one I explained for these two formula, so I taken another one over here, sequence. a plus x square plus ax cube plus so on. Okay, so that means this is the geometric series. Okay, you can see that geometric series means their ratio between two terms it remains same. Okay, so you can take the ratio between a and ax, it is a x square and x cube. Again we got the ratio x, again x cube and x raised to 4, you will get the ratio between two terms x. That means we have ratio between all terms same, then we apply sum of a geometric progression, and this one is infinite term. Okay, and whenever we have infinite term, sum of a geometric progression for infinite term, we write first term it is a here upon 1 minus common difference everywhere we have x here, so 1 minus x. Okay, and this one is a special series. Okay, this one is a special series. When we have addition we consider series, and when we have comma there then we consider sequence. Okay, yes, this one is a special type of a series. It is a convergent. When it is a convergent, okay, when it is a convergent, that x need to be a smaller than 1. So instead of r it is a x here, that x need to be a smaller than 1. Okay, then this sequence, this series is convergent. Okay, yes. So as we are dealing complex numbers, so you need to know z is equal to x plus iy. Okay, and the modulus of a z can be written as square root of first term square plus second term square. Okay, modulus argument, you already have learned this one. Okay, yes, and this one is actually square root of x square plus y square. And if I consider mod z1, okay, actually we know that the mod z which is equal to 1 is the equation of a circle. Okay, this one is the equation of circle. So if you replace mod z1, you can see that x square plus y square, we get the 1 over here. Okay, so mod z which is equal to 1, it is it represent equation of a circle. Okay, and mod z greater than 4, actually what is the mod z greater than 4? Let me explain this one with one page here. I'm gonna explain to you all what is actually meaning of mod z greater than 4. Okay, yes, now see that mod z greater than 4, how I write this is equation of circle. Okay, mod z greater than 4, this one is actually equation of a circle in a complex plane, mod z. Okay, actually we know that z minus z naught, okay, modulus of z minus z naught, which is equal to r. Okay, mod z minus z naught which is equal to r. This one is a standard equation of a circle in a complex plane. Okay, equation of circle. This one is the equation of a circle in the complex plane. Okay, in our complex plane, this one is the equation of a circle in the complex plane. So where z naught is a center, okay, z naught is a center, r is a radii, z naught is a center and r is the radius given here. Okay, yes, now try to take this equation in this form. Okay, so can I write mod z minus 0 greater than 4? Okay, mod z minus 0 greater than 4. Okay, and whenever we are plotting some modulus values, so we convert that inequalities into the equal value. Okay, that means equality. Okay, so see that we have greater than, so we convert first for plotting as equal. Okay, so how am I going to write z minus 0 equal to 4? Okay, so we can see that we have circle whose center is a 0. Okay, center is a 0, and whose radii, okay, whose radii is a 4. Okay, whose center 0 and radii 4. Okay, now let me plot the circle. Okay, so let me plot here circle which is center 0. Okay, this one is a center 0, and whose radius, consider this one is a 4. Okay, this one is the 4 radius. So if it is goes to plus 4 here, obviously it goes to the minus 4 here. Okay, yes, so like this one is the circle. Okay, so let me plot the circle. Okay, so actually we need to know mod z greater than 4 where the value represent. Okay, where this value represent, you need to know this, the how equation look like. Okay, now consider that I do have this circle over here, so I want to represent mod z greater than 4. Okay, so I plot the value for mod z minus 0 is equal to 4. Okay, yes, with the radius 4 and center 0, radius 4. Okay, so I taken the value over here, and now I want to represent that circle mod z greater than 4. Okay, mod z greater than 4. Now we can see that we have modulus of a z and which contain all the value which bigger than 4. That means we have circle whose area, bounded area, whose area, shaded area, we can consider bigger than 4. Bigger than 4 means this outside area, okay, all the area which is outside from circle, okay, it is way easier guys, not the difficult, okay. This is the outside area. So this one is the area, outside area than circle, we represent as a mod z greater than 4, okay. So this one is way easier to understand because already you all have learned this part in your 11-12 standard, okay. Not any issue, it is one of the easier, okay. Yes, so this one is the equation of circle with center 0, radius r, and represent outside circle, okay. Yes. Okay, now one thing need to remember, we are going to apply z transform on a sequence, okay, on some sort of a sequence z transform. After that we have inverse of a z transform also, okay. So we are going to apply z transform on a sequence, okay. Let me tell you some basic prerequisites, that means what you need to know and what we are going to apply in a further chapter, okay. Actually z transform is a very prominent in the analysis of a linear time invariant system. Linear time invariant systems are characterized either by z transform or Fourier transform, okay. Linear time invariant system, okay, what that system, it is characterized into the two part, like one it is in the z transform and another one it is the Fourier transform, okay. And they're characterized, it is related to the location of the poles of a 0. Now poles it is comes, now see that poles, after that zeros, okay, these are the part of a complex analysis, these are the basic concepts guys, okay. Yes, so poles, zeros in their system of function, okay. So already we discussed, okay, Fourier transform, okay, in our last part, okay. Now in our next part we go for applying a z transform on our sequence, okay. So it is not that difficult, okay. So we have to solve actually basic thing here, we have to solve some discrete valued function, okay, discrete system which rise difference equation, okay, discrete system which rise to the difference equation, and their solution as well as their analysis are carried out by using transform technique like a z transform, okay, and it plays very important role for applying these techniques, okay. Yes, so that is here basic prerequisites for z transform. So we go for one more definition, okay, one more definition for z transform that you need to know, okay, and that is very much important here throughout this chapter, okay. Yes, let me explain here the definition of a z transform, okay. So what is the actually meaning of a z transform? Now see that guys, we are going to apply z transform on some sort of sequence. So already you all have learned sequence and series, okay. So what is meant by sequence? Let me explain with the two definitions. Sequence, okay, so what is actually meaning of sequence? Sequence means we write sequence of f of k, okay, sequence of f of k under curly braces f of k, okay. You can consider anything, okay. So like 1 upon 4 raised to k, 1 upon 4 raised to k, I consider 1 upon 4 raised to k as our sequence, and you can consider the any value for k running from 1 to infinity, k running from 1 to infinity, I consider this sequence, okay. Now what actually we are going to apply inside z transform, that we need to know, okay. So I consider sequence f of k as 1 upon 4 raised to k and k running from 1 to infinity, okay. So let's put the value, this one is a sequence guys, okay, this one is a sequence. After that I'll explain series also, okay. Yes, so what happen if k bigger than 1, k greater than 1, that means we don't have the value k as a 1 but bigger than 1, okay? Or you can take greater than 1 also, okay. So we have to include 1 here, okay. So 1 upon 4 raised to 1 means 1 by 4, okay. Need to replace the value for k only, okay. So if k is 1, then we write 1 upon 4. If k is a 2, we write 1 upon 4 square. If k is a 3, we write 1 upon 4 cube. If k is a 4, then we write 1 upon 4 raised to 4 and so on, okay. So if k is a infinity, we write 1 upon 4 raised to infinity, okay. So that is here for the sequence, okay. I hope you all have understood what is the sequence, okay. Yes, so this is called the sequence. Actually we consider this one is the sequence, okay. So in our sequence, in our z transform, we are going to represent the sequence by some arrows, okay, and we are going to define, we gonna define some specific values for the sequence, okay. Now I do have this sequence f of k, Okay, let me explain. This is the basic thing, guys. You need to know about the Z transform. Okay, yes. So if I give the arrow over here, if I give the arrow, okay, over here, so this one is the representation of a sequence using arrows. Okay, so actually this one is the elementary, okay, elementary way to list the number of a sequence. Okay, this is the elementary way to list the number of sequence. Okay, so now we are going to indicate the position, we are going to indicate the position in our sequence. Okay, position in our sequence. Now see that arrow refers, our arrow represent 1 upon 4 cube. So always remember that the other side it represent negative numbers, and this side it represent positive number. Okay, in the form of function. Okay, now see that we can write f of 0. Be careful about here to consider the sequence f of 0. So wherever arrow represent na f of 0, we write 1 upon 4 cube. Okay, f of 0 we write 1 upon 4 cube here. Okay, it's not difficult. The arrow which gives us here na, it start from the 0. So if you go all the way here, you will get the positive numbers like f of 1. F of 1, what is the f of 1? 1 upon 4 raised to 4. Okay, this one is our f of 1. Okay, and 1 upon 4 raised to 5, 6, and other values it comes after this one, f of 2, f of 3, and so on. Okay, so what about for this side? Okay, so if f of 0 it is there, then we write f of minus 1. 1 upon 4 square as f of minus 1. Okay, f of minus 1 is a 1 upon 4 square. Okay, yes, comma, f of minus 2. F of minus 2, I'm going to write f of minus 2 as of 1 upon 4. Okay, so these are the values. So if sequence goes all the way here, the all negative terms represent here these terms. Okay, yes, and all the terms positive here, and it start from the 0. Okay, but now see that, guys, in most of the case we do not have any arrow representation. Okay, so we do not have any arrow representation. Now let me write this f of k sequence f of k as a, I'm going to write that f of k sequence as a 1 upon 4, 1 upon 4 square, 1 upon 4 square, 1 upon 4 cube, 1 upon, okay, 1 upon 4 cube, 1 upon 4 raised to 4. Okay, and so on. Okay, this one is actually 4 square, guys. Now see that we have first term 1 upon 4, second 1 upon 4 square, third 1 upon 4 cube, 1 upon 4 raised to 4, and up to the so on. Okay, this one is our required sequence. Okay, now see that, guys, so we don't have any arrow representation here. Okay, we don't have any arrow representation here. So in this case what we do, we start representation of the number, without arrow. So you have to start from this side only. Okay, from this side. So f of 0 we write 1 upon 4, f of 1 we write 1 upon 4 square, f of 2 we write 1 upon 4 cube. Okay, yes, 1 upon 4 cube, and so on. Okay, you can take 1 f of 2, f of 3, f of 4, and so on here. Okay, yes, see that, guys, I written a sequence here. First form it is arrow representation, second form don't have any representation. Okay, but here you all can see sequence it is the same here, but their representations are different. Okay, if sequence same and their representations are different, then that their Z transforms are different. Okay, so representation mostly matter here. Okay, representation mostly matter here in our Z transform. Okay, so I hope you all have understood. Okay, you all have understood how can we write a sequence. Okay, and it is just expansion of the term. Okay, now let me explain what is the series now. Okay, series is one of the easier. Okay, you already learn about the series. Okay, okay, series, we go for the series. Series can be written as summation. Okay, summation k running from 1 to infinity. We can take summation k running from 1 to infinity, summation k running from 1 to infinity. You can write a raised to k. Okay, this one is our summation. Okay, we consider this one is a series. Okay, so what we need to do, we need to replace the value from 1 to infinity. So we can write, and as we have summation, we have to add the term. Okay, then we write a raised to 1 plus a square plus a cube plus so on. Okay, this one is actually the expansion of our summation. Okay, so a raised to 1 plus a raised to 2 plus a raised to 3 plus all the way to the infinity. Okay, oh, actually this one is the series. I hope you all have understood, guys. Nothing it is difficult. One of the easy term. Okay, one of the easy term. Easy terms are there, a sequence and series. You already learned in your previous class. Okay. Yes. Now we are going to apply. Z transform on our sequence. Okay. But it has the involvement of the series. Okay. It has the involvement of series. Now let me explain Z transform now. Okay. So it is only the definition, it is useful everywhere. Okay, so I feel that is okay here for our today's lecture. I don't want this lecture to be more lengthy, so we go for the definition of a Z transform with some of the example in our next lecture. So I hope you all have understood, guys, our today's lecture, that I taught here some basic definitions. Okay, I hope you all have understood these basic conditions. Okay, so that is here for our today's lecture, guys. I hope you all have understood everything here in my lecture. Even after, if you found anything difficult, guys, let me know in my comment section. I will come up with the similar videos. So thank you everyone. Thank you for my today's lecture.